Good morning, ladies and gentlemen of Precalculus. Good to have everybody here today, except for Kinsey. I hope she's doing well. Anyway, we're going to be working on vectors starting today, and basically, to start out, the question is asked, what is a vector? And a vector is a line segment with special attributes. A vector has magnitude, and a vector has direction. And a vector can be represented different ways, and most of the ways we're going to be using in this class are represented right on this graphic.
Wait, what was it, a line segment?
Line segment that has magnitude and direction. That's what a vector is. Now, a vector can be represented graphically by an arrow, like this red arrow that is connecting 2 points. In this case, the arrow starts at the origin, point P, and goes diagonally all the way up to point Q. Where the arrow ends up is represented by the arrow. And so you call this has different things you call. The starting place vector is called the tail, and this one here, the end of the vector is called the head or tip, but usually head. So that's a graphical representation. Now, a vector can be also represented by 2 capital letters with a little vector segment over it. This particular one means that the vector starts at point P and ends up at point Q. Now, the last thing that is here is this thing right here. We have 7, 6. What do you notice about that? It's not parentheses, okay, so thank you. So these things are angular brackets. And when you see angular brackets, that's a message to you that we're talking about a vector and not a coordinate pair. But you see that this is very similar to a coordinate pair. Like if we wrote this point as a coordinate pair, would we write it the same but just with parentheses around it? Yeah. So this one really means this 7, 6 written as a vector means that you're starting at point 0 at the origin and going up to here. Sometimes you'll see a label referred to, you'll see, and this happens a lot, vector U. They'll have like bold lowercase, U, V, and W are like popular. You remember when we were working on like sides of triangles, they were A, B, and C? Well, it turns out U and V and W are popular, conventionally popular nomenclature letters for vectors. So you'll see those a lot. Does it have to be restricted to those 3 letters? No, not necessarily. Any questions on these? Does this match any of the things you've been working on in physics? Not yet?
We're talking about electricity.
Talking about electricity. I'm talking about, I know you're talking about electricity now, but when you were working with vectors, anyway, maybe there's some remembrance. Okay, question, how can the magnitude of vector U, which now we call this vector U, be determined? Well, it's the distance formula. You remember the distance formula?
Square root of x sub 1 minus x sub x sub 2.
Yeah. So it's this one right here. And even with this formula, it's really simpler than that. It's just like this vector has a horizontal component of, so 6 or 7 horizontally but 6 vertically. And then if we go to our calculator, we can just put those in the calculator, take the square root of both of those, and we get a direction's magnitude. What other word does this thing look like when you look at this vector here besides, what else is this? It's a hypotenuse, very good.
Can you go back to the equation?
This one here? No, back here?
Oh,
Or back one more?
yeah.
Okay, yeah, that's fine. Okay. There we have a component. So this diagonal vector is essentially broken down into horizontal components, and it's broken down like this. You got a horizontal component of 7 and a vertical component of 6, and they can likewise be broken down into horizontal component vectors and vertical component vectors. So this diagonal vector u is the sum of this horizontal vector and this vertical vector. Does that look familiar to physics, what you're doing in physics, right? I hope. We were talking about it. Kaylee asked me a question related to that. And then here in this graphic, what we've done is we've quantified this horizontal component vector u sub x. So here you have this little subscript x, so you pronounce this u sub x, which refers to the horizontal component vector. And then you have u sub y is the vertical component vector. And you see the way that those are articulated with these, like a coordinate pair but with angular brackets. Okay? Hey,
Can you leave it there for a second?
yeah, I'll leave it right there. No. Are you good to go now?
No.
That's some good note takers in here. I had a student today in second period. Everybody was getting their notes out, but he was not. And he said, I really do better if I don't pay my attention to the notes, but just watch what's going on. And that, yeah, you can spend too much attention writing instead of paying attention to what's going on. Okay, next. Now, we have this, you can consider this vector here, vector u, as a line segment rotated up from the origin, can't you? So you can consider that as, like the graphics we have over here, you can consider like this angle here, vector u has like an initial side and a terminal side, can't you? Right?
Yeah.
And so you have an opposite side of 6 and an adjacent side of 7. So the trigonometric ratio that relates the opposite to adjacent is the tangent, which seems to be for vectors the one for direction that you're going to be using more than anything else. So, and to find what the actual measure of the angle is, you get it by taking the inverse tangent. Okay, good. And in this case, when you put this in your calculator, you get about 40.6 degrees, roughly. And what else? There's nothing else new in that picture there. Okay, now we have another little sketch of a vector. And it's going to be this vector v over here. And the vector has a magnitude of 10. That vector has a horizontal component and a vertical component. How do you find out what they are? By taking 10 times the v sub x is 10 times the cosine of 120 degrees. V sub y is 10 times the sine of 120 degrees. So we come back to, don't we, that song that I've been bothering you with all year, right? Our cosine is x and our sine is y. Okay, that's what it is. So the vertical component vector v sub y is going to be approximately 8.66, which is going to be the sine of 120 degrees is square root of 3 over 2. The cosine of 120 degrees is negative 1/2. And so negative 1/2 times 10 is 5. Square root of 3 over 2 times 10 is about 8.66. And we call these things right here, when it's broken down into horizontal and vertical subvectors, if you want to call them that, we call these rectangular components. Why do you think you call them rectangular components? Because they're rectangular and separated by a right angle, okay? Along the x-axis and y-axis, like that. Okay, questions on this? You're still sketching away? Hannah's making detailed drawings. And the use of vectors we're going to examine in this class are ones that you've done somewhat already. Forces. I remember us talking about forces from physics class in this class, right? Navigation and projectile motion. So we're going to just talk about these three uses briefly today, and that'll be our class. Okay, here is a picture of me at home some time ago. I'm sitting on a piano bench, and I'm working on getting down to 190 pounds again, but that's going to take a little work. And so as I sit on that piano bench, my sitting on that piano bench exerts a downward force of 190 pounds. And so that 190 pounds of me sitting on the bench can be represented in two ways. By a downward facing arrow, that's a graphical representation, and by this notation here, 0, negative 190. Does that make sense? Okay. Now comes to talking about Isaac Newton, and we have a little, right above Emily there, we got a little synopsis of the life and experience of Isaac Newton. You see that?
Yep.
Newton's third law. When a first body exerts a force F sub 1 on a second body simultaneously exerts a force F sub 2, which is negative F sub 1 on the first body. That means F sub 1 and F sub 2 are equal in magnitude and opposite in direction. And so as I sit there on that bench, exerting a downward force of 190 pounds, is there another force at work?
Yep.
There is, right? Yes, there's another force at work. And this force, this green vector up here is provided by what?
The bench.
The piano bench. Yes, exactly. And if these things were not equal and opposite, what would be happening to me?
You'd either be floating or on the ground.
Yeah, I'd be either going down towards you know where or up towards you know where. Okay, and we can represent the addition of these two vectors, in this case W and P, algebraically and write them like as an equation. So W plus B equals the sum of these two vectors here. And when you add those two vectors together, it's like 0 plus 0 equals 0, and negative 190 plus 190 equals 0. So your net result of those two vectors together for anything that remains motionless is going to be 0, comma 0.
That's my favorite math equation, 0 plus 0 equals 0.
Oh, is it? Very good. It's one of Mrs. Calkin's favorite songs, too, which is Saved by Zero by the Fix. So this is called an algebraic method of adding vectors. Now, there's also a graphical method of adding vectors. And let me show you this. Because if we have this vector up here, in this, like this, we can move that vector wherever we want. So in this case, we can move it right over the other one to get us right back to the start. So that's what's happening there. Okay, so that talks about forces, and we're going to examine the use of vectors for forces in all directions, right? Not just up and down, but diagonally and so forth. Now we're going to briefly talk about navigation. And thank you. Have I talked to you in this class about p-vang?
I think so.
Yeah, so p-vang, I've talked about it. I know I've talked about calculus, but p-vang is P stands for physical. And so you have a physical situation, which is the plane flying through here. And then you have the articulation of the physical, which is verbal, right? And then you have the analytical, which has to do with the numerical representation of that, or actually the equation, kind of, right? And then you have numerical, I'll put numeric. And then graphical. If I could spell graphical, that would be helpful. And so basically we have this physical, verbal, and we're going to try to make a representation out of this. And here you have the plane flying north on a heading of 300, and what does it mean for it to be a heading of 360 degrees?
Go north.
Well, it doesn't necessarily mean that you go north. It means that's where it's aimed, right? So you're aiming north. But we have a wind that's coming from which direction?
South.
West.
From the left, from west, right? And so that's going to be, so if there's a strong wind, like a south wind blowing outside, and I'm walking to the west, what's going to happen to me? It's going to push me. So I'm going to be aiming that way, and if I don't kind of lean into it and work against that crosswind a little bit, I'm going to be just gradually take me south, or take me north. The south wind will take me north. So this is what this looks like in vector notation. This blue vector here is 0, 500, and this green one to the right is 50, 0. So the question, what will be the speed and direction if there is a west wind? Well, one thing we can do with vectors is we can move them around graphically. So we can take this vector over here and do what with it?
Put it all the way up.
Yeah, we can go ahead and take it. Oops, I moved the wrong one here. There it is. We can move it up here. And then, in that instance, we're going to get our sum of those two vectors is going to be like that, right? starting here and ending here. So the plane is aiming straight north, but ends up over here. And how do we find out how far it gets and what direction it is? P plus W, yes, the distance formula, exactly. So here, we got P plus W, and so the distance formula, which in this case is used by just putting two numbers in the calculator. And then the direction, how can we find the direction? Tangent. And by the way, this magnitude is about 502.5 miles per hour. And here we have theta being, now remember we did the first example, we had theta drawn over here, didn't we?
Yeah.
But here we have it drawn over here, between the line north and the vector of direction. So to find the direction, we take the inverse tangent of 50 over 500. And here it is, about 5.71 degrees. And so we say, and so finally, in direction we say 5.71 degrees east of north is how we finalize that. So that's just a summary of direction of vectors by navigation. And one more thing we want to talk about today is this. We want to talk about projectile motion. Did you talk about projectile motion in physics?
Yeah.
You did? So really what it is this. Okay, you have this thing right here that's thrown in a certain direction, and just as it leaves my hand, and as soon as it leaves my hand, does it have any further force pushing it? No. Okay? When it leaves my hand, what you have is this arrow, this angle of incidence has a certain what? Direction. So let's talk about that a little bit. And then here I have superimposed on this vector and the arc of this parabola, this vector right here with a terminal point of 5, 11, which can be written as a vector with the same thing but in angular brackets. So we have 5 units to the right and 11 units up. And if we know the angle of incidence from the horizontal, and that's called angle of incidence. What else in this class have we called this angle of incidence?
Reference angle.
You know what it is, a reference angle. It's exactly a reference angle because it's right to the x-axis. Thank you. Thank you for connecting. Good job. What else have we called it in this class? For physical representation, we called it a what? Angle of? Angle starts with an E. Angle of, what starts with an E? Angle of, word starts with an E.
The second letter.
L.
Elevation.
Angle of elevation, thank you.
Yes, whoa.
Or angle of inclination too. Okay, which down would be angle of declination. Okay, and then we can find the direction here, which is found by taking the inverse tangent. And so the horizontal component of this vector is 12.083 cosine 65.556, and vertical component is the same thing but sine. And in 5th period what I did is I put this in the calculator to see if that was right. So 12.083 times the cosine of this angle is equal to 5. And so that's where you get this how you can deconstruct. So what we're going to do in this class, we're going to take different angles and put them together. And also we're going to take angles and we're going to decompose them into vertical and horizontal components. And really that's going to be most of what we do for these next couple weeks or so. And then once we get through with this, we're going to get into the direction of the arc. It's going to start here. It's going to come over here like this, like a basketball shot. And that's going to be section 6.2, which is, I think it's 6.2, or maybe it's 6.3, parametric equations. So that is, any questions today? Okay, that's our class.
Well,